Hello everyone. In this short video I want to talk about the nonlinear list squares, which is a method I mentioned in my previous video when I was talking about GPS localization. I used the powerful command in MATLAB, which is lsqnonlin, and so I decided to explain that a little bit more with two examples. One is that GPS example, but the other one is a nonlinear curve fitting, which you might do a lot in your daily applications if you're dealing with nonlinear functions like neural networks, like object tracking, like GPS, and so on and so forth. So I decided to explain it a little bit more. So here you have a function f of x, which is basically it has these sub-functions fi's, and these are those equations that they have to be satisfied. So all of them should be equal to 0 one by one, given the unknown parameter x, and the dimension of this x is m by 1, so you have m unknowns, but the number of equations that you have to satisfy is n equations, and n is quite a bit bigger than m, okay, most of the times, but at least one bigger than m, so your system is over constrained and you cannot get the exact solution, but you can basically get the norm of these individual functions, square them, sum them together, and call it the function f that has to be minimized by selecting the appropriate parameter x, or vector parameter, vector x. Okay, so the goal is to minimize this scalar function f, which is a function of vector x, and minimize this, basically sum of these, square of these residual terms. Now in MATLAB, the command, as I said, is called lsq list squares and then nonlin, which we're going to see. And this lsqnonlin has three different methods that you can apply. One of them is the famous Levenberg-Marquardt, which you use in many neural networks. The other one is called truss region reflective list squares, and the other one is called the interior point methods. So there are three algorithms. Since in one of my previous videos under engineering mathematics and machine learning, I explained this Levenberg-Marquardt, so here I briefly mention it again. Those other algorithms need a video of their own. So the Levenberg-Marquardt algorithm is a combination of the gradient descent algorithm as well as what the Newton-Raphson algorithm, okay? Because each one of these methods, they have limitations. Gradient descent does not take large steps, okay, in flat areas, in the areas where the gradient is small and can get stuck, and on the other hand, take very large step when the function has basically big gradients and it can overshoot the minimum. So setting the learning rate for that is a topic. And on the other hand, Newton-Raphson, the convergence of it, because the gradient descent depends on gradient, as the name said. Newton-Raphson, on the other hand, depends on the second derivative of the function, which we call the Hessian matrix. And the Hessian matrix for a scalar function, which is a function of so many components from x1 to xn, these are the entries of vector x, that is this second order square matrix. Okay, yeah. So the Newton-Raphson uses this del squared, or the Hessian, and it needs to invert it also. And the good thing about it is it's typically fast convergence, but the convergence of that does depend on how good your initial guess is, and it does depend on whether that Hessian matrix is positive definite or not. Okay? The better, the convergence of it gets better as you get what? Closer to the minimum point. When you are further away, it's not doing an amazing job. When you're closer, it's better. On the other hand, gradient descent is the opposite. Okay? So, and as I said, if the Hessian matrix is not positive definite, then you might not converge at all, or if it becomes singular, okay, alone. So that's why in Levenberg-Marquardt, you see something is added. This lambda is added to the Hessian, so it's never singular, so you can take inverse of it. And this lambda parameter is the parameter that controls the weight of this Levenberg-Marquardt being a combination, as I said, of gradient descent and the Newton-Raphson method. Okay, so this lambda is a weight that you change during the convergence of your algorithm. So when lambda is very small, close to 0, your algorithm is literally your Newton-Raphson, and when lambda is very big, it's practically what? The gradient descent. Okay, so what do we do? What we do is we move on with the updates of x and the function, and if the cost function f goes down, which means we are getting closer, right, or the curvature is helping, then we accept that reduction and we reduce the lambda. When we reduce the lambda, which means we are getting it closer and closer to Newton-Raphson, because Newton-Raphson can do a great job closer to the optimal point. So we typically bring lambda down by a factor of 10, by an order of magnitude. On the other hand, if when we update, we see the cost function goes up instead of going down, that means that was not a good update. So we retract the update, we don't accept it, and increase lambda by a factor of 10, so make it closer to the gradient descent. Okay, yeah? So this is the Levenberg-Marquardt. If you want, I have a video on my channel. If you go under my videos under popular, it's one of my top popular videos here, Levenberg-Marquardt, and you see I explain that along with a code and a top function to optimize. And this method is really powerful, okay? So my goal here is not to explain that entirely, although I mentioned it to a good extent. So now we are going to what? We are going to see some applications. The first one, which is related to my previous video, again, if you go back and look at my latest video, it's this one here on GPS and how GPS is working. And in GPS, you have 4 unknowns, which is the bias of your receiver clock as well as the XYZ position of the receiver. And the data that you have are XI, YI, ZI, which are the locations of the satellite that you are receiving information from, and the time of the satellite. Also, this guy here is the time of the signal received in your receiver, and C is the speed of the light. So you have, depending on how many satellites you have n of these. Ideally, these two sides should be equal. This square root should be equal to the right-hand side, but since you have more than 4 satellites most of the time, and you only have 4 unknowns, as I said, X, Y, Z, and B. So your system is overdetermined. So instead of making them exactly equal, which is impossible, you subtract this side and get a residual term. You square it, sum them all up, and the goal is to find these 4 parameters that minimize it. Okay? And here, there is no constraint or anything. So if you look at the code that I uploaded for that GPS video, here I have basically 5 satellites here. But if you want, you can feel free to change some more columns to this X, Y, and Z. And here, this is my point. This is the point on the surface. This is the GPS receiver. And the location for it is given by X, Y, and Z, which we're going to see down here. This is the location of it, right? That's X, that's Y, that's Z. There is some non-zero bias here, which is in the receiver clock, and I set it to 2 times 10 to the negative 4. I have 5 satellites that can get the object can see, and these are these blue points, these blue squares. Their locations are given by this data. And then the difference between this TI tilde and SI, which is the difference time between the satellite clock and your receiver clock, the difference between these two, here, I called it what? I called it delta T. So this delta T has 5 of those numbers, as you can see. And when I also subtracted the bias from these delta T's, so what? So I can basically form this right-hand side. Okay? Now I put all of the X, Y, Z's of the satellites and the delta T between them and the receiver into this vector P. and this p is all known. There is no unknown in it, so I use that p in the function that I wrote for optimization. So x here involves the 4 unknowns of my problem: x of the receiver, y of the receiver, z of the receiver, and b. And p are all of those informations of those 5 satellites. So here you see I have 5 individual equations that ideally should be all 0, but they are not. Yes, you see these square roots equal to c times that time difference. And so my output here of this function is going to be a vector of 5 by 1, where these 5 by 1 are all the residual terms. So one thing you have to pay attention to is this command here, which is called lsqnonlin. This function does not want you to give it that final f. Okay, you're not going to give it this final f. What it wants is the vector of these fi's of x. It wants this guy. It only wants this vector of these fi of x's. It then finds their norm and add them together to form fx. So you don't give it a scalar function, you give it a vector function of the residuals. That's what you should be giving it. And here, if you can see, I call that function my GPS of x of p, which is down here, and I'm using it. I give it some initial guess, which you see it's off from my actual xyz, and my bias I assume to be 0 instead of 2 times 10 to the negative 4. And then I pass that x0 in the function to this lsqnonlin. It gives me the solution as well as the residual norm. Now this guy is really that f of x at the very end. And if you look at it here, you see that the residual norm at the end is 4.8 times 10 to the negative 20, which is practically 0. And you see that the receiver estimated position now that I got my position, GPS solution, the first, second, and third components of that are x, y, z of the receiver. So I compared them against this XYZ, which were the actual receiver position. And if you compare, you see that they are accurate to 4 decimals or more. And if you look at the bias that is estimated, also that is perfectly equal to what? This guy here. Now here everything is perfect, okay? There is no extra noise in my data or anything. If in this function here I add some extra noise, the calculations will not be perfect up to so many decimals, but they're still going to be very accurate. And that I show you in the second example of nonlinear curve fitting. Okay, I add some noise so you can see the effect of that. But this is the first part. This is the first example, which is GPS. And the second example I have here is nonlinear curve fitting. So the function I have is a damp harmonic, right? So it's P1 amplitude times e to the P2, the exponential term, sine of P3t, the frequency, plus P4, the phase, plus some random noise. Okay? So I have some data. I measured some data from a vibration test, right? Let's say, which is the damp vibration of a system. And I want to estimate the amplitude of the vibration, the frequency of the vibration, the phase of the vibration, and this exponential, which is the decaying term, right? That is negative zeta omega n. So if I want to estimate these 4 parameters, right? Clearly you see that my function in terms of p, which is the vector of unknowns, that is a nonlinear function. You see p exponential of p sine of p. And not only that, I want my p to be between some lower bound and some upper bound. So I have limits on how far each one of these 4 parameters can be. So this is the kind of optimization that I want to do. So basically what I have are these red points, these red circles. These are the data I collected from a vibration test. And my goal is to find the parameters of a function, those 4 parameters, like this blue curve, that can fit this data. Okay, so you see I'm not fitting a line or a polynomial or anything. There is no linear list of squares here. It's absolutely nonlinear. So what can I do? Here again, I use this command. Now, before I move on, I want to tell you the syntax of this command. This command is a powerful command, and it has lots of things. The first one is the function that is giving me all of these f1, f2, fn, all these functions that ideally should be 0. x0 is my initial guess. Lower bound and upper bound are the vectors of lower and upper bound on the parameter x. So x should be bigger than or equal lower bound, less than or equal upper bound. Also, your function can have some equality and inequality constraint, like a and b are for equality inequality constraint. So in general, a times x could be less than or equal b, where a is a matrix, b is a vector. And a equality and b equality is for an equality constraint. A equality times x equals vector b equality. And you can have nonlinear equality and inequality. So it's not like your equality and inequality should all be linear like these two. They could be nonlinear. So they are not like a times x equal b or something. That could be a function c of x less than or equal 0 and c equal of x equals 0. So you can have it arbitrarily complicated. And then you have some options here. So that nonlinear con are the c and c equal, but lower upper bound a, b, a equal, and b equal are directly provided if you have them. If you don't have those, you just don't pass anything or pass empty brackets. Okay, so let's look at the second example here. The time goes from 0 to 10. This is my function that I want to estimate. So my amplitude ideal is 2. The damping factor here times omega, and the exponential is negative 0.5. Frequency is 5. Phase is pi over 3. And these are my 4 parameters, and I'm adding some random noise, so it's not as perfect, right? Which is expected in any measurement from any sensor, including vibrations. And now, if you look at my function, it takes the exact same shape as my actual function, of course. So I know the shape of it, I just don't know these parameters, x of 1, x of 2, x of 3, and x of 4. And if I plug in correct vector x, it should generate the corresponding value y, which I have generated, my sensor measurements. And ideally, this whole parenthesis should be equal to 0, but you know it's not. So this is it gives me a vector function, this fun. And then x0 is my initial guess, and lower and upper bound are lower and upper bound on these 4 parameters that I know from my physics or knowledge that I have. I can also pass to it some options. So here I use the command optim options. And I say for this lsqnonlin, the algorithm is truss region reflective. I can say Leavenworth-Marquardt or inner point. Then display iter. So as you move on, the iterations show me the results. Show me the norm of the f and how it is reduced. Even if you want, you can add a plot. Then max iteration, how many iterations before you stop? Here 500. Stop tolerance, that's how much x is going to change between 2 iterations before you say it's literally not moving anymore. And here I use 1e to the negative 5. If you want, you can change them. So now I pass my function x0, lower bound, upper bound, and options, and it gives me back the solution and the res norm, which if you look here when I ran it, you see it only took about 7 iterations for the res norm, or more actually. No, it's more than that. Number of steps. Let me run it again. It does not show all of it here in this thing, but the norm of, well, yeah, in this case it does now. You see 8 iterations, and if you look here, that is 9.13 e to the negative 5, and I guess this is where it is going to stop. And now if you look here, the parameters it estimates are 2.07. This parameter is 2, so you see it's not bad. Then negative 0.52, that's negative 0.5. This guy frequency is 5, it estimated 4.9967, and this guy is pi over 3, right, which is 3.14 over 3, which is 1.04. Here it estimated about 1.03. So you see, it did a very good job. And now if I replot my t-values with this fitted function, that gives you this blue curve. And you see the blue curve does a relatively good job with matching the sensor data. Okay? Yeah? Now, if you have equality or inequality constraints on X or anything like that, you can add them, of course, here as well. But in this case, I don't, so that's where I stop. Okay, yeah? So this is the powerful command lsqnonlin, and it can solve tons and tons of different problems for you if you just give it relatively moderate guess x0. It doesn't need to be perfect, but you see, it does depend a little bit on the initial guess. The good thing with Levenberg-Marquardt is it can accommodate its learning rate, but there is always a chance that you get trapped in a local minima than in global minima. So I'm gonna give you a link to download this file and play with it, and hopefully this video was useful to you. Thank you.